Hello, welcome, good people. Today we are going to be talking about interference of sound waves, beats, and resonance. Now, we'll start today by talking about interference, then we'll talk about beats, and finally we'll talk about resonance. And when we're talking about interference of sound waves, we're talking about what happens when two sound waves are in the same place at the same time. Now, we've already talked about constructive and destructive interference that you see with other types of waves. Like if I had a transverse wave here and another transverse wave here, and those two waves showed up in the same place at the same time with crests lined up with crests and troughs lined up with troughs, well, we'd get what we call constructive interference. And their two amplitudes would add together to make an even bigger wave, like this. Likewise, we've seen before with transverse waves that you could have something like this, where you have one wave that shows up in a place that looks like this. You could have another wave that shows up in a place that looks like this. Those two waves come together, and when they do, you get destructive interference, and so the resulting wave looks something kind of like this. Much smaller than the two initial waves with a much smaller amplitude, Well, we can have the same thing happen with longitudinal waves. Say, for example, that you had a wave that looked like this. Some compressions followed by some rarefactions. Then here's another compression and another rarefaction and another compression here and another rarefaction like this. Say that you had that and it got lined up with another wave like this, where you had a little compression here, a little rarefaction here, a little compression here, a little rarefaction here, a little compression here, a little rarefaction here. Hey, if those two waves ended up in the same place at the same time, what would happen is, and this is very, very difficult to draw, but what would happen is these two compressions would add together and create an even bigger compression. These two rarefactions would add together and give you an even bigger rarefaction. These two compressions would add together and give you an even bigger compression. These two rarefactions would add together and give you an even bigger rarefaction, and so on and so forth. Now, this drawing here that I'm drawing is more of an analogy than anything else. It's not like the wave would really look like this. What you really need to know is that what you would have here is you would have more air getting compressed, and here you would have more air getting spread out. Likewise, you could have a situation where you have a wave that looks like this that shows up in the same place at the same time as a wave that looks like this. If you had compressions lined up with rarefactions and rarefactions lined up with compressions, you would get destructive interference, and the resulting wave would look kind of more like this. All nice and evenly spread out here instead of having regions that are really super compressed and regions that are really not that compressed. You would have an even compression everywhere, and we'd call that destructive interference. Here's a question that I ask my class. I say, hey, if you had a compression lined up with a compression, would you get a louder sound or a quieter sound? And most students will say, well, yeah, you got a compression with a compression. That's going to increase your amplitude. And we know that the increased amplitude of a sound wave corresponds to its volume. So we say that's going to make a louder sound. Then I say to students, hey, you got a rarefaction lined up with a rarefaction. Does that make a louder sound or a quieter sound? This is where students hesitate for a second. But in fact, if you have a rarefaction lined up with a rarefaction, you will get a louder sound, because you have constructive interference, and constructive interference will increase the amplitude. And if you increase the amplitude here, you get a louder sound. Then I ask students, what if you had a compression lined up with a rarefaction like this? What would you get? And they can for the most part, students answer that one correctly. They say you'd get a quieter sound because you got destructive interference here. Hopefully that's tracking with you all. We're talking about interference. Now, students always say, okay, cool, that all sounds nice, Miss Wilson, but when does this ever happen to me? Like, when am I ever looking at interference of sound waves? Well, kind of all the time. If you ever have two sounds that are happening in the same room at the same time, odds are those sounds are interfering with each other, and they're making an interference pattern in that room, where some places the sounds are going to come out louder, and other places the sounds are going to come out quieter. Here's something, though, that is just, wow, it's just so beautiful and so interesting. And what we're going to talk about now, and this is still related to sound interference, is we're going to talk a little bit about headphones. Here, see how I do? Yes. Here I have drawn an AirPod. Now watch this. Now it's an AirPod Pro. So fancy. Now here's the thing is that you all know that something can happen with your AirPod Pros. Here's what you know is that you can put your AirPod Pros inside your ears. You can take out your little iPhone, and then on your little iPhone you can flip a switch. And when you flip that little switch and you flip it to the side, then all of a sudden all the sound turns back on. Yes? You flip the switch, you get noise cancellation. All of the sound turns off. You flip it again, and the sound turns back on, and you can hear all the sound in the world. Well, have you ever wondered, how does one of those things work? Like, how do your AirPods actually get rid of all the outside sounds and then turn all the outside sounds back on again? When I was a kid, when I was really little, we didn't have AirPod Pros. Like, that wasn't a thing that we had. What we had the big headphones that go over your ears. We still have these things. Like, those are still headphones that exist in the world. But that was like the main thing that I remember from my childhood was these big headphones. And I remember if you had noise canceling headphones, they had to be the big ones. Your little AirPods that were going in your ears. We didn't even have AirPods at the time. But your little AirPods that were going in your ears, those didn't do any noise cancellation. You had to have big things like this. And so my thought for noise cancellation when I was a little person is I thought, okay, well, you turn on the noise cancellation and all of a sudden the earbuds, the headphones kind of pump up a little bit and somehow they get a little bit fluffier and they're just canceling out the noise from outside. That's kind of like something of how it works. But now we have these little AirPods and you don't put your AirPods in your ears, click on your noise cancellation and boom, those AirPods just kind of fluff up. That's not what happens. So the question is, how do those AirPods get rid of all the outside sounds? How does noise cancellation work? Let's see if you can understand why and how this works. What you see here with your AirPod, and don't tell anyone that I ever drew an AirPod like this, okay? Because this is like not real AirPod life. But AirPods have two parts. They have a little microphone down here. This right here is your microphone. And it'll only take about 5 years to write because of the lagginess. Then up here, up at the top, you have a speaker. Now here's what happens. You have noises that are constantly coming at you from the outside world. Noises, wait, stop that. Go away. Okay. Noises that look like this. Now, when those noises get to your AirPod Pros, your AirPod Pros can't just like get rid of all those sounds. Those sounds still exist. And most of them will make it through the AirPod Pros and make it into your ear. So you'll see on the other side, you'll get that sound wave, makes its way through to your ear, and you hear this same sound on the other side. Well, here's what happens. When you turn on your noise cancellation, what you turn on is you turn on this little microphone down here. And here's what that microphone does, is this little microphone down here listens to these sounds that are coming in. And then the little microphone tells the speaker, hey, play the exact same sound that's coming in. And the speaker says, okay. And the speaker plays the exact same sound that's coming in. It just plays the same sound right back to you, except when it plays that sound, it plays the sound just slightly shifted over. So instead of having the rarefaction right here, when your speaker plays the sound, it plays the rarefaction right here. Then, instead of playing this compression right here, it plays the compression just a slight little bit behind, just slightly delayed. Then when it plays this rarefaction, it plays it just slightly delayed like this. Like so. So here's what happens. Your speaker plays the same sound, but just slightly shifted backwards, just slightly delayed, so that you get little rarefactions lining up with compressions from the actual sound. Then you have where the actual sound has a rarefaction, your speaker is playing a little compression. Where the actual sound has a compression, your speaker is playing a little rarefaction. And what happens is when you get those sounds together, you get destructive interference here, destructive interference here, and destructive interference here. And all those sounds cancel out so that you hear nothing. Here's something that's great. Here's something that's brilliant. You can put two sounds together and actually get less sound because of destructive interference. What your AirPod does is the only thing it can do, which is play sounds. But it plays sounds just phase shifted slightly off so that those two waves come into your ear out of phase, destructive interference occurs, and you hear nothing. You can make less sound with more sound. Is that not just the greatest thing ever? There's a little bit on interference. The next topic, if you look back at our topics of the day here, we're talking interference, check. Then we're talking beats, and finally we'll end class today talking about resonance. Let's talk a little bit about beats. To show you a little bit about beats, I'm actually going to show you a simulation here, but let's start by talking about what is the concept of a beat. Now, when I was really little, I learned that beats are the things that drums make, and a drum will go like this. And that is the beat. The beat is the bum, 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 bum that the drum makes. But then I got a little bit older, and when I was in about elementary school, I started to realize that actually you could still hear the beat in songs that didn't have drums. And I thought, that is really interesting, because I thought that the drum created the beat. But now I have a song that has a beat to it, but that beat has no drum. And I said, okay, well then, if a beat doesn't come from the drum, then what is a beat? Turns out, the definition of a beat is really simple. A beat is just alternating loud sounds and quiet sounds, loud sounds and quiet sounds, loud sounds and quiet sounds. Now, a drum can emphasize this. Like if you have a drum that goes bum, 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 that's a very clear loud sound followed by quiet sound, followed by a loud sound, followed by a quiet sound. So that can be very helpful in emphasizing the beat. But anytime you get into a situation where you have alternating loud sounds and quiet sounds, you've got a beat. Now here's something that's really, really interesting. Did you know that you can make a beat with a drum, but you can also make a beat just by playing two notes that are really, really close together in frequency? Let me show you how this works. Here, if I go to my computer, yes. Here we have a computer simulation that's going to show you how beats get formed. Now what happens is you play two sounds that are very, very close together. In class, I actually have two sounds, like two little bars, and you can play both of them with a little mallet. And what happens is when you play them both, you can hear this beat between them. But here, I'll show you a little bit of a computer simulation. Now here's what we're going to do. Is you do need to turn on your sound for this activity. If you want to look up this simulation, you can. You can go to its physics. If you type in beat simulations, then it'll come up for you. But it's going to play two different tones. Out of my left speaker, it's going to play 500 hertz. And then out of my right speaker, I'm going to play 501 hertz. These frequencies are nearly indistinguishable. Like if I played them both for you in class and I said, here's 500 hertz and here's 501 hertz, you would hear two frequencies. They'd be like kind of like an A sharp sort of frequency. You'd hear two frequencies and you'd say, those sound about the same. But listen what happens when we play them together. I'll start by playing one individually. This is 500 hertz, listen. Okay. This is 501 hertz, listen. Sounds about the same. Now listen when I play 500 hertz and 501 hertz at the same time. If you listen closely, you'll hear a beat, alternating loud sounds and quiet sounds. Do you hear it? Should sound like a wow, 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 wow. Loud, quiet, loud, quiet, loud, quiet, loud, quiet. Here's why you get a beat in this situation, these alternating loud and quiet sounds. It's almost like you have two runners running a race. The first sound wave can do 500 compressions in 1 second. That's like doing 500 laps around the track in 1 second. The second sound can do 501 laps around the track in 1 second. How many times will the second runner lap the first runner? Did you say 1 time a second? Yes, totally. At 1 time every second. Those two sounds, for most of it, they'll be out of sync, but 1 time every second, they'll be in the same place at the same time. And you'll have constructive interference because the compressions and the rarefactions will line up with each other perfectly. Until, once again, the 501 hertz gets going a little bit faster and goes ahead of the 500 hertz. But right for a second, you're going to hear those two compressions lined up perfectly. There's also going to be a second point in time when the two runners are on perfectly opposite sides of the track, when you have a compression that is perfectly lined up with a rarefaction. When that happens, you'll hear a quiet sound because of destructive interference. So here's what you hear. Every second, you hear 1 time when you hear a really loud sound and a second time when you hear a really quiet sound. That means you hear, on average, or I shouldn't say on average because it's always the same. You hear every single time 1 beat per second. 1 loud sound and 1 quiet sound, and 1 loud sound and 1 quiet sound, and 1 loud sound and 1 quiet sound. 1 time every second. Check this one. Answer this question. What would happen if I played on my little simulator here? What if I played 500 on one of the speakers and 502 out of the other speaker? Do you have a prediction for what would happen? Let's see if you're right. Did you say that you would hear a beat frequency and you'd hear 2 beats per second? Because, yeah, that's exactly what you'd hear. Now these runners are lapping each other twice every second. And so you hear 2 beats every second, 2 times when you get constructive interference and 2 times when you get destructive interference. What if I made this instead of 2? What if I made this 6? Now give a guess as to what you'd hear. Did you say you would hear 6 beats a second? For sure, you hear the back and forth and back and forth and back and forth 6 times a second. Take out your stopwatch and time it. You'll see that every single time you're hearing 6 of those every single second. 6 of those every single second. Now, here's where things get really interesting. Here I have 500, and here, what if I change it pretty significantly and make it something like 900? Take a quick guess. What is going to be the frequency of the beat that you're going to hear between these two? Did you say 400 hertz? For sure, you're going to hear 400 beats per second. Hey, does 400 beats per second still sound like a beat? No, you know that 400 hertz is within the range of human hearing. It doesn't sound like a beat anymore. If you're going back and forth 400 times a second, that sounds like a sound. That sounds like another note. Here's something that's fun. You can take 2 frequencies that are right next door neighbors with each other, play them at the same time, and you'll get a third frequency that underlies them, a third note. This is very difficult for students to hear, and this is a kind of demo that really favors those who are musically minded, who have good music ears. Like if you've been listening to different notes and different frequencies and different pitches for a good amount of time, then students can hear this one better. If this is all kind of new to you and you've never really done that kind of thing before, then this is harder for students to hear. So here's what I'm going to do, is I'm going to play them at the same time. What you should hear when I play 500 and 900 hertz at the same time is you should hear a lower frequency that's at 400 hertz. To show you what this is going to sound like, here I have a little, I'm going to simulate for you, this is what 400 hertz sounds like. So, in the background, when we play 500 hertz and 900 hertz, you're going to see if you can hear this sound that is kind of underlying the other two. Are you ready? Here we go. Can you hear it? It might be hard to hear, so here's what I'm going to do, is I'm going to play this one at the same time, and then I'm going to hit play on the 400 hertz. Then you can kind of get a sense for what the 400 hertz is going to sound like. I'll turn off the 400 hertz, and you can see and listen if you can hear the 400 hertz still kind of fizzling on in the background, okay? So here's both of them. Here's these two with the 400 hertz. Now you're going to listen to see if you can hear the in the background, even after I stop playing this one. Could you hear it? Whew, tricky to do, but some of you can hear it. Some of you who are my musical people say, whoa, that was crazy. Good stuff there. Hey, that's a little bit on beats. The next thing that we're going to talk about today, and the final thing that we're going to talk about today, is resonance. To do this, I'm going to have to show you a little bit of a demonstration here. Don't worry, it's nothing too crazy, but I think it's very helpful. Let me get these things out of the way here. Here, I have a pendulum. This pendulum is hanging from the top of my pendulum stand like this. Now, here's what I can do, is I can take my pendulum, I can pull it back this way, and I can let it swing back and forth. This pendulum has a natural frequency, which is a frequency that this pendulum likes to swing back and forth at. And if I pull it back at any height, it'll swing back and forth at its natural frequency, like so. You know that the natural frequency of this pendulum depends on the length of the pendulum. So it'll swing back and forth. Now, could I make this thing go back and forth at some other frequency that's not its natural frequency? Sure, here's what I would do. I could grab this thing like this and I could go like that. That's what we call a forced vibration, because I forced that thing to vibrate at something that's not its natural frequency. But if I just let this thing go of its own free volition, it's going to vibrate back and forth, or I should say oscillate back and forth, at its natural frequency, or what we call its resonance frequency. Now pretend, what if instead this wasn't actually a pendulum on a string, and what if instead this was a kid on a swing? And the kid on the swing said, wow, this is so fun, Miss Wilson, let's go even higher. I would say, okay, and at first I'd let the kid go, then I'd push and push and push and push, and I'd push on the kid every single time that the kid comes back to me. So the kid would come back, I would push, then the kid would come back, I would push, then the kid would come back, and I would push. Hey, do you see how the frequency of my pushes would equal the frequency of the swing? If the swing's swinging back and forth really, really fast, I'd push more often. If the swing's swinging back and forth really slow, I'd push less often, because I'd push every single time the swing came back to me. This is what we call resonance. Here's the idea. Resonance says if you vibrate something, if you push on something at its natural frequency, at its favorite frequency, you'll increase the amplitude of that vibration, just like a kid swinging on a swing. If you vibrate something at its natural frequency or at its resonance frequency, you will increase the amplitude of the vibration. One more time so that you can get it written down. This is a little something about resonance. If you vibrate something at its natural frequency, the amplitude of the vibration will increase. If you vibrate something at its natural frequency, the amplitude of the vibration will increase. Pause that video if you need to get that definition written down. Here's how resonance works. Resonance works, actually I'm going back to the camera here, sorry to like that. Here's how resonance works. It turns out that it's not just pendulums here that have a natural frequency. It turns out that all things really have a natural frequency. They have a natural frequency that they like to vibrate back and forth at. Let me show you an example here. Here I have a tuning fork that's connected to a wooden box. This tuning fork has a natural frequency that it'll naturally vibrate at. Just like how if I pull the pendulum back, that pendulum will naturally swing at its natural frequency or its resonance frequency. In the same way, if I hit this thing, it'll naturally swing, or it'll naturally vibrate at its natural frequency, at its resonance frequency as we call it. I could make it vibrate at some other frequency if I wanted to. Like I could take this thing and go blah, 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 and we call that a forced vibration. But that's not its natural frequency. It's not its natural frequency of vibration. Now here's what I'm going to do, is I'm going to just strike this little tuning fork here, and you're going to hear its natural frequency. That's it. That's the natural frequency of this tuning fork. Its favorite frequency to vibrate back and forth at. Now, here's what we're going to do, is we're going to talk a little bit about resonance. Here's how resonance works. Resonance happens when you push something back and forth at its natural frequency, and so it starts vibrating back and forth even bigger. It'll vibrate back and forth at the same frequency. The frequency that it vibrates back and forth at won't change. In other words, it's not like it's going to start vibrating back and forth way faster, because that would violate its natural frequency. It'll keep vibrating back and forth at the same frequency, but it'll vibrate back and forth at the same frequency way bigger, with way bigger amplitude. It's like, again, if you're pushing that kid on the swing, they'll swing up way higher. The amplitude will increase, but it's still going to take the same amount of time for them to get back to you. They're still going to do the same number of swings per second. So, with resonance, what happens is you take the object and you vibrate it at its natural frequency, and it's going to vibrate bigger, with a bigger amplitude. I'll show you an example. Okay, here we go. Get over here, buddy. Okay, and you get out of the way. Okay, here we go. Oh gosh, well this is just embarrassing. Oh wow, okay, no one said these videos were fancy. Why are we paused? Okay, everybody good? We all good? Everything's happening? The world is a good and happy place? Okay, that's what we like to see. Sorry for our transition time, good people. Here's what I have. I have 2 of these tuning forks connected to boxes. Here's one, and here's the other. They are exactly identical, Watch what happens. Now, when I put my hand on the tuning fork, it should completely stop the vibrations. Listen and see if you can hear all the vibrations stop. Do you still hear those vibrations a little bit? Now here's the issue, is I don't frankly know if you can over the computer, but if you were here in person, you would say, wait a second, Miss Wilson, you said that after you did this and stopped it, all the vibrations would stop and I wouldn't hear anything anymore, but I'm still hearing things. I feel like I can still hear it making the same sound. Why? Can you still hear this guy? No. But you can hear this guy. Here's what happens. This thing vibrates back and forth at its resonance frequency. These 2 guys, because they're identical, they have the same resonance frequency. They have the same favorite frequency. So this guy vibrates back and forth at his natural resonance frequency, and when he does, he compresses and decompresses the air. That compression of air then travels all the way over to this little buddy right here and presses on him back and forth at the same resonance frequency, at the same frequency as this guy. Well, since they share a resonance frequency, when this guy gets vibrated by the same frequency, it's like pushing that kid on a swing, and he starts vibrating back and forth way more. And then, even when I stop this one, you can still hear this one. Why? Because he's vibrating at his natural resonance frequency. Do you see how if having two of these would actually make one of them louder? Because if I have two of them, when I hit this one, you have to excuse me, I left my mallet all the way across the room. When I hit one of them, here, this one also vibrates. So I get a bigger amplitude because it's not just one guy squishing the air anymore, now it's two guys squishing the air. Guitars are built this way. If you have a guitar, the base of that guitar, the body of the guitar, is built so that its resonance frequency matches the resonance frequency of one of the strings on your guitar. So you strum your guitar and the whole body vibrates. It makes the sound much louder because the vibration is not just coming from that little string, it's coming from the string and it's coming from the body of the guitar. Here's the only thing though, is that a lot of students say, wow, that is magical. You just made a sound louder out of nothing. Well, not out of nothing. Here's the problem, is that we can't just create energy. And as you know, amplitude corresponds to energy. We can't just increase the energy for nothing. So here's what happens, is that all resonance trades amplitude for duration of the sound. What happens is, if you have more resonance, the amplitude of the sound is greater. In other words, it's much louder, but the duration of the sound is shorter. The sound doesn't last quite as long. So the sound sounds louder, but it won't continue to ring out for quite as much time. So all resonance is going to trade out loudness for duration of time. Hopefully that makes some sense to you. Now, here's something fun. Here are a few other fun facts of things. One last fun fact about resonance. You can find the resonance frequency of nearly anything by figuring out at what specific frequency that thing makes the loudest sound. Let me show you an example. Stay right there. Here I have a paper towel roll. Now this paper towel roll also has a natural resonance frequency, and when it gets hit with that natural resonance frequency, it'll vibrate like crazy and make a much louder sound. So you can do this at home, this is something that you could try. Try a series of frequencies all the way up and see which one makes your toilet paper or your paper towel roll vibrate the most. That one is its resonance frequency. Here's something else that's fun. You've seen those videos before, you've heard those stories about when opera singers will sing and they'll break glass. Why does that happen? Well, because if you get to a high enough pitch, the pitch of their voice will match the resonance frequency of the glass. The glass, because you've hit its resonance frequency, will start to shake back and forth like crazy. And when it shakes back and forth like crazy, it eventually can't handle its own shaking and it shatters. We've seen this happen with bridges before. In 1940, not a history teacher, in 1940, a bridge called the Tacoma Bridge collapsed because the wind started pushing on the steel bridge, and the wind blowing that day just so happened to push the bridge at its resonance frequency, like a kid on a swing. That bridge swung back and forth more and more and more crazy until all of a sudden that bridge collapsed. And there were no casualties except for a dog. Tragedy. So that's a little bit on resonance. Hopefully, as we went through this lecture today, this is kind of a difficult lecture to take notes on because there aren't a lot of things that actually go on this page here. But my hope would be that you found some things that were important and you listened to the things that were important and you wrote them down. We talked about interference, beats, and resonance today. Interference happens when you have two sound waves that show up in the same time. Compressions and compressions add together to create bigger compressions. Rarefactions and rarefactions add together to create bigger rarefactions. When you got constructive interference, you get louder sounds. When you got destructive interference, you get quieter sounds. Then we talked about how that applies to noise-canceling headphones. Next, we talked about beats and how you can get a beat that comes from just playing two different frequencies at the same time, and how you can even use two different frequencies played at the same time to get a whole new note. And finally, we talked about resonance, how resonance happens when something vibrates at its natural frequency and the amplitude of its vibration increases. We talked about how this happens with guitars, how this happens with our tuning forks, and how you could even do that with your paper towel roll at home. And there you go. That's a little bit on interference, beats, and resonance for today. I hope you have a wonderful, wonderful rest of your day. Bye, good people.